from your local news leader, Karina Rubio, Matthew White, and Central Illinois' most accurate forecast with meteorologist Jack Griffin. You're watching The Morning Show at 9 on WCIA 3.
Welcome back to The Morning Show. We're actually not done talking about the James Webb Space Telescope. After all, there's plenty to see in the sky this year.
That's right, and joining us this morning to talk about that is wise guy Paul Cleott. Paul, thanks so much for joining us this morning. Now, you've been on a few times to talk about this telescope, so what's the latest update?
Yeah, so, right, the whole point was that I mentioned before was that on Christmas Eve, actually, this was launched into space. And then on New Year's Eve, the sun shield, which is the thing in the bottom that was deployed. So that was a big deal because technologically very difficult. And what happened in the last couple weeks is now that they've deployed both the secondary mirror, which you can see coming down in place there, and then also unfolded the rest of the primary mirror. That'll happen in just a second here. So that's the one side, and then the other side. And just to get a sense of scale, that sun shield is about the size of a tennis court, and the there we go. And the entire mirror itself, the main mirror, is about 21 feet across. And the bigger the mirror is, of course, the more light it can collect, but also the better resolution you can get. And so this has a resolution of something like 0.1 arc seconds. But it turns out if you want to look at exoplanets, so those are planets around other stars, that's still not probably good enough to actually be able to image the individual exoplanets. So I'm just showing here, what a typical star might look like with a bunch of planets going around a star that's some distance from us. And the red arrow shows sort of the best that you can resolve. So all of those things would sort of look like one blur. You wouldn't really be able to pick out the individual things. And yet we still want to be able to find out about these exoplanets. When an exoplanet goes in front of a star, it blocks out a little bit of the light, so that's how we can tell that there are exoplanets, and of course that happens periodically every time the planet goes around. We'd also like to find out what those planets, what the atmosphere might be like. And so in order to do that, we need to use a different piece of information here. So the fact is atoms all have their own sort of spectral signature. It comes from the fact that the electrons around the atoms can only be in certain energy states, kind of shown here on the left for hydrogen. And any light that we see from any element comes from an electron at some high energy state falling to some low energy state, and then the photon energy has to match the difference between those. And every element has its own signature. And in fact, I brought kind of a fun little spectral lamp here, shown here. So this is a light, and at the moment you just see some kind of a pinkish purple light. But the other thing I have here is a grating, and a grating is a device that will spread that light into its different colors in different locations. And so you can see off to the left and also off to the right, kind of a bright pink and a blue line. There's kind of a green one in between. If instead I look at something like helium, I can go to my next one here. Helium has a completely different signature over here. So now you see it's got some yellows and some greens. It's kind of a cyan. I'll just do one more, maybe a very familiar one. This is neon. So neon, of course, has all of these red and orange and yellow lines. Okay, so we can use that. If we could measure those different lines, then we'd be able to tell what the atmosphere was made of. Let me just go back to my slide here. So, the top bar here is what I've just shown you. I have a hot gas, and then, sorry, the top one is just like the sun, so just a continuous spectrum. In the middle is what I just showed you, where we have a hot gas and we see these particular lines. Now, that's not what we have with these exoplanets. Instead, that gas is relatively cold, and it's the light of the sun passing through that gas that then scatters. Anything that's resonant to those transitions is scattered mostly off to the side. Some of it is also scattered to us, but mostly it's scattered off to the side. So there's actually a reduction at those particular lines. And so this is how we can think about that happening to detect something, is when the planet goes in front of the star, it blocks a little bit of light. It scatters some of the light away, and different colors are scattered different amounts depending on, again, what the content of the atmosphere of that exoplanet is. And so, depending, we might see, for example, something that has water lines, or methane or carbon dioxide, things that would tell us about the atmosphere of an exoplanet. So it is still going to be a little time before we actually get data. The Webb Space Telescope still has to, I think, about another month and a half till it gets to its final location, which is about 1 million miles away from us. But then it'll start taking data to look for exoplanets, to look back in the universe using its infrared imager, and it should be very exciting.
All right, thanks so much, Paul. Definitely excited to see all that it discovers, but thanks for joining us this morning.
It's always a privilege, Paul.
Bye-bye.
Jack has your forecast up next, right after this quick break. We'll see you in just a few minutes.